Hello and welcome to The Explainer. Today, we're going to teach a computer how to tell the difference between flowers. And we're going to do it with just a little bit of data and a really powerful idea for machine learning. Okay, let's dive into this.
So here's the puzzle we're going to tackle together. It sounds simple, right? Can a computer learn to tell flowers apart just by their measurements? Now, the tricky part is we're not giving it any pictures. No photos, just raw numbers. How long the petals are, how wide the sepals are. So can a machine really learn to see the difference just from a spreadsheet? Well, we're about to find out. To solve this puzzle, you really only need two things. Two key ingredients. First, you need a good set of examples for the computer to study. That's our data. And second, you need a smart way for it to learn, and that's our tool. To get started, we've got to structure our information in a really specific way. On one side, we have what we call features. Just think of these as the clues: petal length, petal width, and so on. And on the other side, we have the labels. These are the correct answers we want the computer to learn. In this case, the actual species of the flower. The whole goal here is for the machine to figure out the hidden patterns that connect those clues to the right answer. So what is this tool we're going to use? It's something called a Random Forest Classifier. Now, just imagine you have a really tough question. Instead of asking one single expert who might have a blind spot, what if you could ask 100 of them? And then you just go with the most popular answer. That's exactly what a random forest does. It combines all these votes from lots of different decision makers so it doesn't get tripped up by one bad opinion. It makes the final prediction way more accurate and reliable. So just how big is our committee of experts? Well, in the actual code, there's a setting, it's just a parameter called n estimators, and we set that to 100. And that literally means we are building our forest with 100 individual decision trees, and every single one is ready to cast its vote. All right, let's head over to the training ground. This is where the magic happens. This is where our machine learning model goes from knowing absolutely nothing to becoming an expert at identifying flowers. It's study time for our computer.
This code uses the iris dataset to build a random forest classifier. First, it loads the data, separates features, sepal and petal measurements, and labels, species, then encodes species names into numbers. The dataset is split into training and testing sets. A random forest model with 100 trees is trained on the training data and then tested. The model achieves 100% accuracy, meaning it correctly classified all test samples. Finally, it shows the mapping of numbers back to species. 0 equals setosa, 1 equals versicolor, 2 equals virginica.
Now, before we even think about training, we have to do something that is, and I mean this, absolutely crucial. We split our data. 70% of it becomes the study material. This is all the information the model gets to see and learn from. But the other 30%, we hide that away. It becomes the final exam. This is so important because it means the model can't just memorize the answers to cheat. No, it has to truly learn the underlying patterns to have any hope of passing. So when you put it all together, the whole learning process is a pretty clear 3-step recipe. We've already split the data, and we've created our model. So now comes the most important part, the actual training. Using a simple command called fit, our model gets to work. It studies all that training data, meticulously building connections and learning the subtle differences in measurements between, say, a setosa and a versicolor flower. This is the moment the learning actually happens. Okay, training is complete. Our model has studied hard, and now it's the moment of truth. It's time for the final exam. Can it use what it learned to correctly identify flowers in that 30% of data that it has never, ever seen before? So we hand the model the measurements from our hidden test set, but we keep the answers to ourselves. Now, based purely on its training, it looks at each flower's petal and sepal dimensions, and it makes a call. I think this one is a virginica, or this one looks like a setosa. It's making its best guess. And now it's up to us to grade the test. And the result? A perfect score, 1.0. That means 100% accuracy. Think about that for a second. On data it had never seen before, our model didn't make a single mistake.
That is a flawless performance.
Okay, so a computer can identify flowers. That's kind of neat, right? But why does this simple little example matter so much? Because this exact process, this workflow, is the foundation for solving much, much bigger and more complex problems out there in the real world. So let's recap what we've learned because it's really important. We've seen firsthand that you can teach a computer to classify things as long as you give it labeled examples. We've learned that you must separate your data for training and testing. And we saw how a model like the random forest uses the power of a committee, that collective wisdom, to get incredible results. This basic workflow, train, test, predict, it's used everywhere, from medical diagnoses to spotting financial fraud. You know, this quote really just hits the nail on the head. It gets to the very heart of what we just did. If our model had only memorized the training data, it would have totally failed the test. That perfect score proves it didn't just remember stuff. It actually learned the underlying patterns well enough to apply that knowledge to completely new flowers it had never encountered.
And that really brings us to our final thought. We started with a pretty simple question about flowers, right? But by teaching a machine to see patterns in simple measurements, we've unlocked a technique that is unbelievably powerful. So the question I want to leave you with is this. If we can achieve this level of accuracy on a task like this, what other, much more complex patterns in the world are just waiting out there to be discovered and understood by a machine?